is Nikhil, verified educator on Unacademy. Follow me on Unacademy Learning app. In this particular lesson, we will be dealing about symmetrical fault analysis problems from previous GATE and ESE questions. So make sure that you have watched the previous two lessons on fault analysis before watching this particular video, because that will be introducing you what is fault analysis about and theoretical aspects regarding symmetrical fault analysis. So let's get started. Hey guys, let's get started with this fault analysis problems. Okay, the target audience for this particular lessons are GATE, IES and PSU exam aspirants and people preparing for conventional paper exams like IES mains or civil services mains, SSC JEE paper 2, or practicing power engineers, and also students, engineering students can also benefit from this particular course. And this is me, Nikhil. You can read about me by pausing the video. And this is my Unacademy profile. You could follow me. There are 8 more awesome courses waiting for you. So let's get started with today's lesson, that is problems on symmetrical fault analysis. So please follow this particular instructions to derive maximum benefit. Okay, so immediately pause upon seeing the question. Okay, try to do the solution on the whole on your own and then see the whole video solution and verify the answer. What I am telling is, don't directly skip to the solution in order to just verify the answer, because my way of solving the question might be easier than you know. It might be time saving, it might include any shortcut also at times possible. And also GATE aspirants, please keep your GATE online calculator either in your smartphone or laptop ready with you to solve the problems. And also PSU and IES aspirant need not keep any calculator, just make freehand calculations practice. Okay, and semester students and these IES and CSE mains can use their scientific calculator, because you are allowed to use your calculator. Now let's start from first question. This question is from UPSC IES 2000 year. An isolator synchronous generator, okay, with the transient reactance equal to 1 per unit, 0.1 per unit on a 100 MVA base is connected to a HV bus through a step-up transformer of reactance 0.1 per unit on 100 MVA base. The fault level at the bus is. So according to the given question, this is going to be the single line diagram. He says that there is a generator connected to a HV bus using a transformer. He is given the reactances value. So I can convert this reactance diagram, this single line diagram into its reactance diagram by just indicating its reactance. This is the generator with its reactance, and this is the reactance of the transformer, and this is the high voltage bus. He asks you to find the fault level at the bus. Fault level at the bus means if the fault takes place at the bus, what is going to be the fault level. So I am creating a artificial fault at this particular bus, and I will determine the fault level, or which is otherwise called as short circuit capacity. We know the short circuit capacity is equal to base MVA by per unit reactance or impedance up to the point of fault. So up to the point of fault, what is the reactance available? These both reactances, right? 0.1 plus 0.1. So 100 MVA is the base, is already given, 100 MVA base by 0.1 plus 0.1. This is going to be 500 MVA. Option B is the right answer. Now in the next question, let me read out. A 50 MVA 10 kilowatt 50 hertz star connected unloaded 3-phase generator has a synchronous reactance of 1 per unit and subtransient reactance of 0.2 per unit. If 3-phase fault occurs close to the generator terminals, the ratio of initial and final values of the sinusoidal component of the short circuit current is. So the answer is going to be 5. It is asked from GATE 2016. Okay, according to the given question, this is the data available. Okay, he has given the synchronous reactance and he has given the subtransient reactance. So he is asking you to find the ratio of initial to final. So I hope you remember, this is the oscillogram of the short circuit current when this kind of short circuit happens at the terminal of the generator. This initial current, this initial period is called subtransient period, and what is the final period? Steady state period, isn't it? Initial is subtransient, final is the steady state. Therefore initial current is called subtransient current, final current is called nothing but the steady state current. And the subtransient current and steady state current have been given by this equation we have already seen in our last videos. Okay, so E by X double dash E by XD, that is the subtransient current and synchronous current. You see the current is inversely proportional to its reactance. So I am just going to take the ratio of these both. I double dash by I, that will be equal to synchronous reactance by subtransient reactance 1 by 0.2 as given in the question. So 5 is going to be the answer. Okay, 5 is the ratio. Hope you understood this question. So you have to keep some important points in mind, okay, before doing the problems, okay. The main aim of questions asked in this particular topic, that is symmetrical fault analysis, is to make sure that you will obtain the value of fault current. It could be in per unit or actual value, or fault level, which is nothing but the short circuit capacity. It might also be in per unit or MVA rating. What we have to do is, we have to do all the calculations in per unit system only. Okay, do all the values in calculations in per unit system only, convert all the actual into per unit, and finally present the answer in actual or per unit as asked in the question. If we ask you to present in per unit, put it in per unit. If we ask you in actual value, convert into actual value. And also one of the important thing is pre-fault voltage consideration. So what should be the pre-fault voltage? Because we know already, we have discussed that we are going to convert the reactance diagram into a Thevenin's equivalent considering the point of fault. So what does the Thevenin equivalent will have? It will have a Thevenin voltage as well as the Thevenin reactance. Thevenin reactance is nothing but the reactance up to the point of fault. That is easy to calculate. But the challenge is about Thevenin voltage. Basically, Thevenin voltage is nothing but the pre-fault voltage. Before the occurrence of fault, what is the voltage at that point of fault? That is what the Thevenin voltage is. And we have to find out it also in per unit value. And it is very important finding this thing. Okay. So in a generator, basically you in a power system, while doing this kind of problems, take the terminal voltage V. Okay, V as a base voltage, please. Okay. Now we know that we will do this fault analysis in two cases before the occurrence of fault. It might be unloaded or loaded case. When unloaded, okay, your Thevenin voltage is going to be nothing but the internal generated EMF. Okay. Please remember another thing. Okay. VTH is nothing but EG. Before the occurrence of fault, or internal generated voltage is always VTH equal to, because this is the EG only which is will actually supplying the fault. Okay, EG is the actual voltage that is actually supplying the fault. We have already discussed about this in the last video. And under unloaded case, we also know that internal generated voltage equal to the terminal voltage. Since terminal voltage itself is a base, okay, you have to take EG or VTH as 1 per unit. So this is a direct shortcut, okay. Not every textbook, not many textbooks will mention about this. Whenever you have to solve this kind of questions, find out whether it is a loaded or unloaded case. The moment you discover it is unloaded, forget about finding VTH or voltage, per unit voltage. That is always per unit, 1 per unit, okay. And finding the Thevenin impedance is a quite easy thing. And if it is loaded, this is not going to be the case, because if it is loaded, the internal voltage and terminal voltage are going to be differed. Okay, the internal EG will be V plus J I naught XL. What is I naught? Pre-fault current. That is nothing but the load current. And this X value can be anything, subtransient or transient, depending upon the type of fault current asked. Then you have to find out the new EG. We have also discussed about this thing also. And here also you have to take always V as 1 per unit. And EG will be greater than 1 per unit. This also keep in mind, okay, in loaded case. Now let me do this problem. Asked from GATE 2001. A 50 Hz alternator is rated at 500 MVA 20 kV with XD, that is synchronous reactance 1 per unit, subtransient reactance 0.2 per unit. It supplies to a pure resistive load of 400 megawatt at 20 kilovolt. The load is connected directly across the generator terminals. When a symmetrical fault occurs at the load terminal, the initial RMS current. Initial RMS current means subtransient current. Okay, you have to take only subtransient current into consideration before doing the problem. So you just determine before the occurrence of fault what is the state of the system. Before the fault, the system is loaded, directly mentioned, and this is what you can deduce the diagram or the circuit of the given system before the fault. There is a generator which is supplying a resistive load, and the resistive load capacity is 400 megawatt, and it is supplying at a voltage of 20 kV. Now I want to find out what is the pre-fault current, okay, before the occurrence of fault. That is our main aim. Okay, whenever you are finding in a loaded case question, immediately find out what is the steady state current before the occurrence of fault supplied to the load current. So load current, first let's write down the power expression for load. P is equal to root 3 VL IL cos phi. This is a 3-phase system. It is a resistive load, hence cos phi equal to 1. So IL equal to P by root 3 VL. So P is 400 MVA. I am going to write it down like this, and I am going to get 20 into 10 power 3 by root 3 amps as my load current before the occurrence of fault. Now after fault, what happened? fault is occurring at the terminal of the generator. That is what he says. Okay, terminal of the load. That means at this point, then the load will get disconnected. Now the short circuit current will be flowing from the EG, XG dash dash and into the fault, and it will be circulating like this. And what can you say? What is the value of I double dash or subtransient current? Subtransient voltage by X per unit. Okay, what is subtransient voltage is equal to, we have already seen, terminal voltage plus pre-fault current into XD dash dash. Okay, please keep in mind this is XD double dash, subtransient reactance. Now all values are in per unit. Okay, V is 1 per unit, we know. XD dash dash is 1 per unit, is already given. Okay, 0.2 per unit already given in the question. We have the actual value of load current. We need to find out the per unit current. So in order to find out the per unit current, I0 per unit value is always equal to actual value by base value. Actual current by base current. Actual current is known here. I need to find the base current. So how to find the base current? So base current will be equal to base MVA is equal to root 3 base voltage into base current. Please remember this formula. From this, IB equal to SB by root 3 VB. So put the values, you will get 25 into 10 power 3 root 3 amps as the IB value. Now I know the actual value of load current, base value of the current. Per unit current will be actual by base. Putting this and solving, I get 4 by 5, that is 0.8 per unit as my pre-fault load current in per unit. I will find out the pre-fault internally generated EMF, that is V plus J I0 into XD dash dash. V is 1 per unit always, because I told the load voltage or the terminal voltage must be the base. If it is the base, then it is 1 per unit. And put the values, we are just concerned about the magnitude. EG dash dash as 1.0127. I double dash will be equal to EG double dash by, that is internal generated EMF by X per unit, reactance up to the point of fault. Only reactance up to the point of fault is there, that is XG dash dash, subtransient reactance. Put the values, you get 5.063 per unit as the answer. This is the answer for this particular question. Okay guys, thanks for watching this video. In the next video, we will be continuing with other awesome questions in this particular topic only. Please follow and enroll to my course. Okay, follow me on Unacademy. Please like, rate and review if you like. Okay, if you like this course, okay, rate with 5-star and write an awesome review. Recommend and share this course with your friends. Comment your opinion. I'll be attending it. And have a nice day finally. Thank you.